Yeah, so we'll get into Embankments, Reservoirs, quite a bit, especially the
Hello? Can anyone hear
hydraulic
me?
structure can be added to any model with a blended. Basically, special weak pipe
Hello?
network. You can have more than one in a together.
That's all right.
You gotta do the PowerPoint in one hand and talk.
All right, sounds good.
You gotta talk them, so.
It's easy enough.
Just keep them.
Yeah, okay, so, let's get back on track here. So, we'll look it over there. So, all right, so structure types, broad crested weirs, two different types, culverts, circular and rectangular, active control structures, scheduled discharge, like if you have a dam, you have a measured, you have a gauge at the discharge of the dam, and you can put that in your model. You do that a lot. Generic structure rating curves. And so, so horizontal weirs, using this equation listed here. So stay on track though. And if you want to put in a weir, you can, like Chuck said, go look at the wiki, figure out how it's done, play with it, try to get it to run. Sag curve weirs, also by this equation listed. We haven't used these a lot, but especially if you're in engineering with nature projects for a site, weirs are popular. Different 6 different culvert types listed here. Schedule releases, specific discharge as a function of time, history matching with known releases. So for example, we have one of our bigger models we're doing, the Santa Ana River. There's flood control dams at the edge of the mountains. And so the Corps runs those dams. If you're calibrating to historic data, then there's historic measurements of how much water is released in the dam. Get those as a function and basically a time versus the flow, and have that in your model. And those are easy. Those are is an easy way to do it. You also have a rating curve based on an elevation and a discharge. So if you have that data, you might use that as well. Either way, you can simulate any hydraulic structure or flow control device. You can have multiple compound structures. You can have weirs together, as well as several different types of weirs together, and each structure element allowed to have a different invert elevation. So you can just mix and match these as you would desire. So this is an example of an embankment in Judy's Branch, which is one of the, there you go. So embankment added along the freeway, which you can add in GSSHA. The red line here represents the embankment in WMS. And here's a culvert location, so you could have an embankment as well as a culvert. You can have several culverts along this embankment along the freeway. Culvert, and this is how WMS would represent it. And it's a certain type of link at a culvert, and then you would click on that link, and it would display a menu that would show you what kind of culvert you have there and what kind of culvert you could add to it. And here's an example of the hydraulic control structure menu. You can see different selections you can make. Plug in your values based on the as-built, or if it's a planned project, then what they're thinking of putting out there. And then on to lakes, reservoirs, and tension basins. This is a powerful tool, a useful, very useful tool in the GSSHA model, in that lakes and reservoirs and detention basins are dynamic features that exist both in the 1D stream network as well as the overland flow plane. So the lake itself, oh, here it's come back. So the lake itself exists both in the 1D stream network as well as an overland flow plane, and the lake can shrink and grow and take up cells in the model that become lake cells and don't become overland flow cells anymore over time. So the lake is completely inside the model, and that provides, especially for reservoir operations, some very useful useful techniques to be able to use. So reservoir fluxes, you got your rainfall, overland flow, stream flow, ET, outlets, discharge, and then seepage, groundwater recharge in and out of your reservoir. And like interaction with the overland flow plane, reservoirs occupy overland flow cells and can grow and can take a cell over time and then discharge it. Water flows from overland flow cells to the reservoir and from the reservoir to overland flow cells. So as your lake grows, if you get a lot of a big rain event, that water can run off the overland flow plane and into the reservoir, and the reservoir basically can grow and shrink, taking overland flow cells. So no cell processes occur when, so if a lake takes over an overland flow cell, then then that becomes part of the lake, and it's just part of the lake, and there's no more overland flow processes or infiltration or ET going on in that cell anymore. Reservoir stream interaction. A reservoir is a boundary condition in the stream network. Flow from streams to reservoirs and from reservoirs to streams. So like we said, we can go in and out. Reservoir overtakes stream cells when the overland flow cells contained them are taken. And reservoir release stream cells as overland cells. The reservoir releases stream cells as overland flow cells are released. So as the lake shrinks, then it would release those cells. Creating reservoirs, defined in one way to do it is define it in the stream network with a polygon embankment that represents the dam. So you put it in an embankment. You can specify an outlet structure, and then you would specify a minimum, maximum, and initial water levels, which of course would change over time. So you need to create whatever period you're calibrating to. You would have to have those correct values for an initial water level to run your model. Okay, another way to do it is a stage area volume relationship that is calculated directly from the grid and WMS. So that would be something that you get usually get that from the owner of the lake you're interested in. They're going to have calculated that, or somebody would have calculated that. And WMS can show you the plots of the relationships.
So you can either get it from, you can be given a stage area volume relationship, but if you don't have it, the grid, it'll pull from the grid, which is not as accurate.
But the grid becomes a percentage.
That's right.
Is the key there.
Yeah.
So unless you have a really good description of the elevations below the lake and a fine grid, you'd be much better off to get the relationship.
Yeah, but WMS also has tools for getting that relationship.
Yeah, to pull it off the grid.
Yeah, it gets it off of, you can get it from the DEM, the elevation. And if you have elevation data for your reservoir.
Yeah, so there might be.
You'd have to have the definition if it's a reservoir, it's
Yeah.
just a detention basin. Probably got it.
So with all the different options, have you tried to do like pumping scenarios within GSHA? So let's say, let's say you had a detention pond and you want to exit where you want to pump water out of it to another location.
Yeah, we've done studies. You can pump from anywhere to anywhere. The overland from the stream or from the groundwater. You can pull it out. You can put one in a negative one or a positive. So you pull out stream, put it on low, pull out stream, put it in the groundwater. Whatever.
Okay, so here's an example of a Galley Reservoir up, it's in Wisconsin, I believe. So, come back, sorry. So here's this watershed with the reservoir down at the bottom, with the stream network. So typical, the light blue area is the initial cells, the purple area is the minimum cells, and then the red line would be the embankment. And WMS would show that to you.
One of the notches right here, when you draw the embankments, WMS is gonna find the nearest edge of a cell to make the embankment. So that's why there's a small sort of conceptual difference between the line you draw and where it actually is. And sometimes that can mess you up if you don't realize that they're two different things.
Yes, the embankment sits on the face of a cell and it blocks the flow between the cells until the water level gets above the top of the embankment, then it flows over as the progress of the year. So that's how it actually works. So that's what you draw it in, but it's going to snap it to the nearest face grid cell. You want to make sure that like didn't get inside your reservoirs.
Yeah, or you put your outlet on the other side of the.
Yeah, you gotta be a little careful when you put the embankment in the structure together. They line up just so.
Yeah, I can go.
Okay, so here's an example of Galley Reservoir. This is their elevation discharge curve that they have for the lake, for the reservoir. I don't know if this is going to run or not. Should, huh?
Yeah, it's a good idea how it expands and contracts, and then how it takes the stream and then gives the stream back up. How it's like a dynamic model as opposed to a static model that you find in those models.
Okay, one more time.
One more time.
Did a lot of other kind of.
That is kind of slick.
Yeah, never keep one.
Uh-oh. Okay, so here's the little more detail on this. So Galley, this is the initial condition, and then there's a maximum flood. There's a flood grid file that GSHA outputs. You can get the maximum extent. And then the stream discharge associated there with that reservoir. And the reservoir level and volume curves.
But that's output. That's all output.
Output,
from
yeah.
irrigation.
These are outputs, yeah. All right.